Any questions about anything? Well, I thought I'd start out with a problem to review a little bit about the definitions from last time about limits. Let's take a fun one. I want to show that the limit as x tends to c of the square root of x is equal to the square root of c when c is a positive. I need c to be positive for the square root to make sense. And so if you're going to do it straight from the definition without using any facts, the first step is always to say let epsilon be bigger than 0. It could be a really small epsilon. And then what we want to analyze is how close x needs to be to c to make x minus the square root of c. I won't write absolute value yet, but I want to make that small within the tolerance of epsilon by getting x close enough to c. And we've had a number of problems where we have square roots like this, a difference of square roots. And there's a classic trick to multiply by something that'll make that difference of squares to get rid of the square root. So the clever trick is to realize, aha, if I multiply this by 1 in this form, then I get a difference of squares on the top, and that would be the square root of x squared, which is x minus the square root of c squared, which is c. And on the bottom, I get a plus instead of a minus, which is good when you're trying to estimate something. And so, using that trick, by the way, I give you some practice problems where that trick is appropriate for the exam. But using that trick, I can see that the distance between the square root of x and the square root of c is x minus c, and that's what I'm going to have to make less than delta. I have to choose a delta to make this. Okay. So let's see, to make sense of this, I better at least assume that x is positive. So the square root of x makes sense. So I'll assume x is positive, so square root of x makes sense. And let's see, I want to estimate that somehow. Let's think. That's going to be less than, I'm adding a square root of x in the bottom. I don't like that, because then I have to think about square root of x. But I'm adding it in the denominator. So this is actually less than 1 over just the square root of c part times x minus c. And here's where I realize I'm getting somewhere. I can easily make this less than epsilon. So I want this less than epsilon. And I can make that happen if my x minus c is less than so this is less than delta. And let's see. So what I want now is delta over the square root of c to be less than epsilon. And so what I need is that delta, anything less than epsilon times the square root of c, is going to work. So if x minus c is less than epsilon over c times the square root of epsilon, and of course in the definition you need to specify that x is not equal to c. Then the square root of x minus the square root of c is less than that given epsilon. And that's what it means for that limit to e to the square root of c. Questions about that? So it's kind of tedious to go through the epsilon delta definition. And so some theorems about limits will be welcome to avoid doing this over and over again. There's some simple facts that I want to spell out now that make sort of here's an annoyingly difficult thing to do. To say that a limit doesn't exist. I'll say DNE, that's math for does not exist. Or is not equal to L. Is a mouthful because when you start negating for every epsilon there is a delta, you know, if you say not for every epsilon there is a delta, that means, okay, there's an epsilon where something goes wrong. And then when you have to say for that epsilon there does not exist a delta such that blah, it means that there's some, yeah, if you start trying to do it, it gets nasty. Is a mouthful because of all the quantifiers. Quantifiers are all, every, there exists, etc. So the next thing I'm about to tell you is a handy little fact to avoid having to go through that process. Handy fact is let's suppose that f is defined on an interval AB and C, so it's a AB into the real numbers, and C is a point in AB. Then the limit as x goes to C of f of x is equal to L turns out to be equivalent to the fact that every sequence of point of x that tends to C, f of that sequence tends to L. So let me see if I'll say it properly. For every sequence xn, where, of course, the xn's are where this thing is defined, xn's are in AB, and all the xn's are different from C. The limit as n goes to infinity of f of xn is L. Okay? It's very it's fairly straightforward using the definitions to demonstrate this fact. I guess the most interesting one is that I'll let you read that in the book. It's fairly straightforward. And I kind of went through a similar argument last time about the cluster points piling up. Okay, so if you want to show that something doesn't have a limit, you just have to find a sequence where it gets weird. And a fun example of that, this function leads to a bunch of fun examples. Namely, sine 1 over x. Okay. You know the graph of the sine function. It starts out at 0, and then it repeats at 2 pi, etc. So it's 0 at 0, it's 0 at pi. Next time it's 0 is 2 pi. Next time it's 0 is 3 pi, etc. This is the graph of sine of theta. And let's see, it's equal to 1, for example, at pi over 2, 2 pi plus pi over 2, etc. And then it repeats. Okay, so let's think about when is 1 over x equal to n pi? That happens, of course, when x is 1 over n pi. And 1 over n pi is a sequence that tends to 0. And at those points, sine 1 over x would be 0. Okay, so this would be an xn, and the sine of the xn's, sine 1 over the xn's would be equal to 0. And these tend to 0. So I found a sequence tending to 0 such that the sine of 1 over xn is equal to 0. That's not... And now here's another sequence. Let's take 1 over x equal to the places where the sine is 1. Let's see, but the first one was pi over 2. Why don't I do it like this? How about I start with 2 pi? I'm going to take 2 pi times n plus pi over 2. I guess I could take n equal to 0 there also. Here, I'll fix that. I don't like taking n equal to 0. I want to start with n equal 1. So I'll take it to be n minus 1, n plus 1. What do I want to do? Oh, n minus 1. That'll start out at 0. Plus pi over 2. Well, xn is 1 over that. X, rather, is 1 over that. And so, and that goes to 0 again. Plus pi over 2. That goes, easy to see that that goes to 0 as n goes to infinity. Let's call that x sub n. And so in this particular sequence, sine of 1 over x to the n, they're all equal to 1. So I've got one subsequence where the sine of that subsequence tends to 0. In fact, it's identically equal to 0. So it certainly converges. And another subsequence that goes to 0 where that thing converges to 1. And in fact, I could find you anything between minus 1 and plus 1 to make that happen. So the important point here is these are unequal. They're different. So, without doing the epsilon delta agony, I can tell you that the limit as x goes to 0 of sine 1 over x does not exist. Okay, and you can believe it when you try to graph this thing. It's a fun thing to graph. Let's see. The sine function is bouncing up and down between +1 and -1. So that's a +1. That's a -1. And let me graph the sine function. I'm going to graph sine 1 over x. Kind of wiggles normal, but then 1 over x gets bigger and bigger, so it's just blasting out along the positive real axis, and this would start piling up, filling in the whole interval from -1 to 1. And then the negative sine of minus x is minus sine of x, so the other side would be minus of that. The book has an actual graph of this thing, and then it would just pile up and fill in. It doesn't actually fill in that space there. It gets so dense that it looks like it's filling in that space. And I just found you a subsequence that tends to 0, and a subsequence that tends to 1. And in fact, I could find you a subsequence that tends to any point in this interval from -1 to +1 on the y-axis. Okay. Questions about that? Let's see, I'm going to talk about limit theorems. And one of the best limit theorems around is the squeeze theorem. For limits of functions. And so suppose we have functions. You need 3 of them for the squeeze theorem. I'm going to squeeze something between 2 other ones. So let's suppose we have f, g, and h on an interval AB, and that C is in AB. And we have a squeeze inequality. So we have f of x is less than or equal to g of x is less than or equal to h of x for x unequal to c. And then the condition is if this one tends to L and this one tends to L, so if as x tends to c, then of course the g gets squeezed in between there. Then the limit as x goes to c of g of x, the thing in the middle, exists and is equal to L2. And it's pretty straightforward to demonstrate that from just the definitions of limits. And so here's another one of my favorite examples. I like that sine 1 over x function. So let's see. I'm going to graph x times sine 1 over x. Okay. Sine 1 over x bounces up and down from between being plus 1 and minus 1. And so I'm going to graph here x and minus x. Let's see if I can do a better job. There's a graph of minus x. Okay, and sine 1 over x is bouncing up and down between being plus 1 and minus 1. When it's plus 1, it would be on the top x curve. And when it's minus 1, it would be on the orange minus x curve. And it's going to start bouncing like hell as you get closer to the origin. All right? And over here, it would be minus, well, let's see, x is an odd function, and sine 1 over x is an odd function. So over here, it would actually be a symmetric picture, bouncing up and down between plus 1 and minus 1. See if I can do a better job this time. I like that. And it certainly looks like it's getting the squeeze there. What are the functions I'm squeezing that between? I have that purple thing, I have an orange thing, but the curve that's the top curve is orange on the left and purple on the right. What's that function? Absolute value of x, yeah. And the other side is the minus. So we see, let's see, the curve on the bottom is minus the absolute value of x. That's less than or equal to x times sine 1 over x. And that's less than or equal to x, absolute x. And of course, it's easy to show that absolute x and minus the absolute x tend to 0 as x goes to 0. Let's see, this is for x unequal. That thing's not defined at x equals 0, but now I see what I should define it as. I should define x sine 1 over x, a function, to be 0 at 0. That would make it continuous. We're going to talk about continuity in the next lecture. So this goes to 0. This goes to 0 as x tends to 0. And so the sign, let's define, it would make sense. I'll define h of x to be equal to x sine 1 over x if x is unequal to 0, and 0 at x equals 0. Then it's nice to see that h is a nice continuous function. It doesn't do any jumping at the origin. And so with this h, the limit as x tends to 0 of h of x is equal to h of 0. There's going to be a word for that. It's going to be it's continuous. Okay. But once you start playing around with this particular example, you tend to get carried away. Here's my favorite example. Example in this genre. You don't see genre in a math class very often. e to the minus 1 over x squared sine 1 over x. Okay, so that's if x is unequal to 0. And e to the minus 1 over x squared dies away incredibly fast as x goes to 0, because 1 over x squared goes to infinity. And so it looks like e to the minus infinity. That's a very fast dying away function. And so you can bet that you can make it continuous at 0 by setting it equal to 0 at x equals 0. And then when I graph this thing, I'd have graphs, I have to graph e to the minus 1 over x squared. Let's see. E to the minus almost 0. I wish I didn't. It looks kind of like this. I'd have a plus version of the curve. It's so small here and dying away so fast that if you really graph it using a computer, it looks like it's actually 0 in an interval. Okay, let's see if that would be symmetric. So that would be the graph of e to the minus 1 over x squared. And then there'd be a version of it below that's symmetric. This would be minus e to the minus 1 over x squared. And then the sine 1 over x would do the usual wiggling between the top curve and the bottom curve. And it will wiggle infinitely many times as it gets squished into the origin. Let's see, this is another one that would be an odd function. Mo is better on the left. Well, that e to the minus 1 over x squared dies away so fast that you can start using the squeeze theorem to compute derivatives of this thing. And you can show that the derivatives exist. And in fact, all the derivatives exist. So all the derivatives, including the ones at 0, exist and are continuous. Even at x equals 0. There's some work to do to actually show that. But that's a mind-blowing example because, after you study power series and sine and cosine and e to the x, and even things like square root of 1 x minus 4, those all have power series expansions. And so you think, oh, maybe every nice smooth function can be expanded as a power series. This shows you no such luck. That's a infinitely differentiable function, and all the derivatives vanish at the origin. So the Taylor series would be the 0 series. So the Taylor series is a big fat 0, but the function isn't identically 0. So it's not equal to its Taylor series. So not every function can be expanded in a power series. Every C infinity smooth, that's the word for that infinitely differentiable thing. Not every C infinity smooth function can be expanded in a power series. That's kind of disappointing. If you look at the early papers on power series, they got really excited about them. That's an important fact to know. Questions about anything? I guess I summarized above something I should have isolated as a fact. That that convergence criteria about subsequences is a nice thing to know, but when I used it, I actually used it in a divergence setting. So I'll call it a divergence criteria. The limit, as x tends to c, of f of x does not exist if and only if I can find a sequence so that if and only if there is a sequence xn with all the xn's unequal to c and xn tending to c as n goes to infinity, such that the limit as n goes to infinity of f of xn does not exist. Okay, that's easier than trying to negate all the quantifiers in the statement of does exist. A limit does exist. So it makes it an easier task. And that's what I used above. I could have taken those sequences and sort of merged them together. Let's see, I should maybe say my example of sine 1 over x. I got you a sequence where, so above, I got an xn tending to 0 with sine of sine of 1 over xn equals zeros. And I called them both xn last time, but now I'll call this one a yn tending to 0 with sine 1 over yn equal to 1. And so if I wanted to give you a sequence where those things don't converge, of course I could merge them together. So I'm thinking out loud here. How would I merge those two sequences together? Oh, I'd let the xn's be the even terms. I'll call them z. z sub m, I'll call it z sub n, equals x sub n when n is even, and it would be equal to yn. Well, let's see. What am I trying to do here? X sub n here's what I should be doing. It's n over 2 when n is even. And I'll make this n over 2 plus 1 to minus 1. No. What am I trying to do? If it's odd, you know what I'm doing. Yeah, so here's how when you try to write something like this and you get gunked up, let's let a sequence Zn be equal to, the first spot is x1, the second spot is y1, the next spot is x2, the next spot is y2, etc. Then that sequence I would have two subsequences and they converge to different things. Questions about that? Yeah.
So you have Zn equals x of n minus un, y of n minus odd.
Well, I chose different. Evidently, when I wrote it this way, I made it the reverse.
That would still work though, right?
Yeah, that would work fine, except I got myself jumbled up trying to think about how I would write a formula for the coefficients. I should have written z2n and z2n plus 1. And then it would have made sense to me, probably. Let's see, I should point out, the book is much more careful in their language. When you start trying to think about functions on weird sets, like sets of functions on sets, like, let's see, what are the typical sets you run across? Well, a finite set would be kind of dumb. There wouldn't be any concept of a limit on a finite set. But a set like 1 over n, such that n is a natural number, then it's natural to talk about the limit of the function at 0, because 1 over n is 10 to 0. And another set that's going to come up is the rational numbers, Q. Okay, those have lots of limit points, and so it's natural to think about the limits at limit points. And so that's why the book, we just defined accumulation points last time. And so the definition, let's suppose if C is a cluster point or accumulation point. It's an accumulation point. Point of a set S in the real numbers. F is a function defined on S to the real numbers. Then the limit as x tends to C of f of x equals L means it's the most natural thing you could possibly do, but then you have this irritating thing that your function is only defined on S. Means given any epsilon bigger than 0, no matter how small, there is a delta such that it looks exactly the same as the definition we've given before. F of s, little s, minus L is less than epsilon when, okay, s, little s, of course, needs to be in the set, big S. S should be unequal to C, and it should be within delta of C. Okay, I mentioned last time there's infinitely many points in a little delta neighborhood like that in S, so there's infinitely many S possible in this to check in this inequality. Okay. All the theorems I've been talking about go over for this more fancy definition, including the divergence criteria and the sequences business. I just didn't want to say this every time I state stated anything. And the squeeze theorem, for example, they all go through. So remark, all the theorems and facts we've studied carry through for this more general definition. Okay. And to illustrate why you might want to need this fact, let me do an example here that's kind of fun. Let's let f of x, this is a classic example of a function that comes up in real analysis. Let it be equal to 1 if x is irrational and 0 if x is rational. Well, there's countably many rational numbers, and there's uncountably many irrational numbers. And when you study measure theory, rational numbers are a set of measures 0 in the real line. And irrational numbers are a set of full measure. So, for example, in the unit interval, the irrational numbers have measure 1, which is kind of like saying length 1. And the rational numbers don't amount to anything. They have 0 mass from the point of view of measure and length. And so you think of, well, that function is really just 1, and this being 0 on rational is no big deal. But this function is not continuous anywhere. And you can show the limit doesn't exist at every point. And let's do it. I'm going to use that divergence criteria. So I claim here the limit as x goes to c of f of x does not exist at any c. Okay. How would I demonstrate that with what we've done today? Well, C, I don't know if C is rational or irrational. I want to find a sequence of rational numbers that get close to C and another sequence of irrational numbers that get close to C. And remember, we showed that rational numbers and irrational numbers are both dense. And so here's, for each n, here's what I'm going to do. For n, a natural number, I'll have c minus 1 over n is less than something, is less than c plus 1 over n. Okay, c minus 1 over n and c plus 1 over n are two real numbers. And therefore, by the density statement, there would be a rational number. Q, I'll call it Q sub n. I'm going to pick the Q sub n in there. Q sub n in the rational numbers. And I can do that because they're dense. And then also I'll do the same thing. I got the c minus 1 over n less than something less than c plus 1 over n. I'm going to pick an irrational number. I guess I can call it Rn for real, but not rational. So here I'm going to pick an Rn which is real but not rational. So Q, that's irrational. And then I've got two sequences. One of the sequences, the function is always 0, and the other sequence is always 1. And therefore, it doesn't converge. So I can, once again, I can merge these two. The QNs are different. They're all, oh, let's see. I should, if I'm going to do this and make it work, I better specify that this QN is unequal to C. That's easy to do because there's infinitely many in here. Heck, I don't need to do it. Why don't I do it like this? I don't want it to be equal to C. So I'll just have them to the right-hand side. And the irrational numbers are also dense. And so now I can merge those two. The QNs are unequal to C, and the RNs are unequal to C, and they both tend to C. And now I can merge those two in a actually, this merging trick is so simple and obvious that I could make a new divergence criterion. If I find subsequences that converge to two different things, the series diverges. So I would merge them of Q1, R1, Q2, R2, etc. I get a sequence where the value is 0, 1, 0, 1, 0, 1. We see the limit does not exist. Okay, so here's a fancier divergence criteria. Criterion. If you can find two subsequences that converge to two different things, two subsequences as above, they have to be different from the point C. Convergent to different things. Let's see. F of the subsequence. Convergent to two different things. Then, of course, the limit doesn't exist. Oh. I got carried away. I have a whole other page of facts to show. I'll save it for next time. There's some really simple facts that I don't want to waste your time because they look so similar to things you've shown. So read about the easy facts. In 4.2, like the limit of a sum is the sum of a limit. Stuff like that. Just writing it down. My hand go numb. Etc. And the proofs look exactly the same as when we did it for sequences. So there's really not a lot of, you should read them and study them and believe them, but I don't want to waste time in class doing them. I'll state them next time just to be careful. Any last minute questions about anything? Homework 6 is due tonight. I'll be on Piazza if you have any last minute questions.